Okay, should be up and working. So tonight I wanted to talk a little bit about SWR, and this is just I've gone over a lot of this material before, but this is maybe just a little bit different direction on looking and thinking about SWR and how it plays into our profession here. So the topics that we're going to go through is a little bit of history, so we'll understand a little bit about how this came into play, what SWR is, and how do we measure SWR, and how does SWR affect our operation? All pretty simple topics here. So on the history side, in the old days when transmitters were made from vacuum tubes, some of us still remember what those things look like. And both the exciters and linears, all of those things were all made from vacuum tubes, but matching impedance between transmitter and antennas was really not a concern. So back in the old days, it's like, well, whatever you could do to connect up wire and get it to work and get it to make apparent RF was always just good enough. So tubes were able to handle a wide range of mismatch in impedance. They just seemed to work. They didn't get bothered by what happened when impedance weren't exactly matched right. So that changed when solid state transmitters started to be used. So when solid state transmitters started coming online, that was a game changer, and our knowledge of what went on how we fed antennas really changed. Before World War II, we used ladder line for our feed line. So everybody used ladder line, and that was just the way we did it. And there was some pretty cut and true formulas and methods for producing ladder line that seemed to work pretty decently for us. And ladder line by itself is a pretty forgiving product as far as mismatching of impedance. Now in ham radios, we typically use coax that is 50 ohms impedance. The way we adopted this standard, and this has really become a standard for ham radio, after World War II, there was a huge abundance of surplus coax available to the ham radio operators. So ham radio operators, being that what they are, they saw a really good deal, saw some cheap feed line, and they went out and got a whole bunch of that, and that just automatically evolved into what we have for today for the standard for ham radio. All of our feed line for coax, almost all of it, is virtually all 50 ohms. With our new solid state transmitters and coax for transmitting for transmission lines, we now find ourselves concerned with SWR. This is a new thing that kind of popped in, and we're concerned about what that transmission line and that whole path there did for impedance. And we have mismatch impedance. SWR comes in. So let's talk about SWR. SWR is expressed as a ratio. It's always a ratio. SWR represents how efficiently RF power is transmitted from our power source, in other words, our transmitter, through our transmission line, that's our coax, into a load, and that load is always considered the antenna out there. So what we always strive for efficiency of 100%. So everything that comes out of that transmitter gets through our transmission line and into our antenna, and 100% of all that RF that we create in our transmitter ultimately gets transmitted. Well, that's a novel thing, but that doesn't always work for us. This requires the source impedance, the transmission line, and the load have exactly the same impedance. One thing that I think we all kind of have learned is that impedance is really, really important and that whole production, or that whole line of things, our transmitters, our feed lines, all the connectors, the impedance up at the antenna, all of that has to match. If any one thing throws a little blip into the problem, we have an impedance mismatch, and that causes us some problem. There is a mismatch in impedance of any of the components in an RF path, transmitter, coax, connector, then blah, blah, blah. Just read those things off. Some of the power, and then some of that RF may be reflected. It's really not maybe, it will get reflected back to the source, back to the transmitter. So it acts like an echo. That means whenever we send out some power from a transmitter, that isn't a perfect feed system, that has some kind of mismatch in impedance, we will get reflected power. And not 100% of that stuff is going to make it to the antenna and get sent out as RF. Reflected power is RF energy that is not radiated from an antenna. That's a really important point to remember there. Reflected power is RF energy that is not radiated from the antenna. The all-important part is getting that to be radiated from the antenna. SWR can be thought of as a ratio between the total RF power from a transmitter and the RF power that is reflected and doesn't get radiated by the antenna. So that's all basically SWR is. It's just basically a ratio between what goes out of the transmitter and what ultimately gets radiated from the antenna. There's a little bit more that goes into it, but that I think is a pretty good principle just to remember that. If you have SWR, that generally means you're not getting everything out. As the SWR value increases, less of the transmitted power gets radiated at the antenna. So let's look at a really cool chart here. So this is this chart is based off of an exciter that creates 100 watts out there. So that right-hand column kind of shows how much of that 100 watts is getting out. So let's say we have an SWR of 1.5 to 1. That's pretty normal. I think most people end up with antennas and feed systems that are usually about that efficient. That means you have about a 4% loss. So out of that 100 watts coming out of that exciter, you end up dropping about 4 watts out there. That's pretty darn good. Now understand there's other losses in there that are not really being talked about, and even through coax, you can have resistive losses that can also add to this as a problem. When you get to a 2 to 1, you got 11% worth of loss. When you get to a 3 to 1, you're at a 25% loss. Only 75 watts are making it to that antenna to be radiated. So that starts to get a kind of a little on the painful side. So I think everybody knows that when they start seeing something that getting up into the 3 to 1, there's probably something you want to try and do about it. But there are situations you can't do it. And you can see as we move all the way up, if we get to a 6 to 1 SWR, we only get about 50% of the power that actually makes it to the antenna to be radiated. Pretty low. So let's take a look and see what some of this means here. Modern transmitters, modern solid-state transmitters don't like a SWR above 3 to 1. And this is kind of a generalization. What you find is that some transmitters, as you start surpassing an SWR of 2 to 1, it'll start cutting back on the power that it produces, because that SWR comes back and it actually increases the power dissipation that those MOSFETs in the transmitter have to dissipate. So it causes a heating problem really quickly there. not all transmitters have protections for high SWR. So, most everything that you buy these days, all have something kind of protection in there. If it sees a bad SWR, it'll cut back on power. Some of them will just end up giving you a fault and just say, hey, I'm not going to produce anything. The SWR is so bad out there. But some of the older rigs there just don't have a real good SWR protection in there. And that can cause a real problem. It can be pretty easy to take and burn up the finals in a transmitter.
Hey, Mike,
No.
and maybe this is a little premature. I don't know if you're going to talk about SWR when there's an antenna tuner or coupler in the midst of your system. And because SWR can be fabricated to a point, and I don't want to misuse the word, but will you maybe address that before the end of the presentation?
You mean the slide that just came up?
You know, you didn't pay me to do this, but it was a delay because of my mega herding machine, and I see it now.
Okay. Well, I needed a drink of water anyway, so.
Okay.
Thanks for the diversion.
Sure. Wow. Okay.
So let's
I think it's
talk
time for a new.
so let's talk about an antenna tuner, because that's, well, I can't say that everybody has an antenna tuner, but it's really hard to find antennas that does everything. There is no one antenna that does everything that you need. I mean, if you want to work 40 meters, if you want to work the phone band and you want to work the digital side, you need 2 antennas. If you want to work 80 meters, you need 3 antennas that are cut to the right frequencies to be able to get from one end of that band to the other end of the band. And then same way up at 160, you need at least 2 antennas to be able to work the upper phone part and another antenna to work the old digital, the lower end of that thing. So there's never a perfect antenna there that does everything. So we seem to always drop back to using an antenna tuner. So generally an antenna tuner is used to improve the impedance between a transmitter and feed line connected to an antenna. So you can have a good old antenna out there that has a pretty gnarly, 3-to-1, 4-to-1, 5-to-1 SWR on it in, let's say the digital side, but up at the phone side, it works just fine. And as it 2-to-1, which you don't need the darn tuner in there. But if you want to get on digital and you don't have infinite amount of property and you can put up antennas for all different parts of the different bands, that's fine. But that's not real life. So that antenna tuner is going to help improve the impedance. So then antenna tuner, so a transmitter wanting to see a transmitter always wants to see 50 ohms, period, for impedance. With an antenna tuner, you're trying to make the transmitter happy by making it think it is transmitting into a 50 ohm load. So that's cool for the transmitter. Now you've satisfied him, but the other end of that antenna tuner that is now connected to your feed line and ultimately your antenna up there, it's still seeing the funky SWR. So here, if you have an antenna system coax connected to an antenna with a 3-to-1 SWR, the antenna tuner will keep the transmitter happy, but you are still wasting 25% of your TX power. You still have that mismatch in impedance, and it's going to be reflected back at the antenna tuner. And guess what? Who's the guy that has to dissipate that 25% of that, or that 25 watts that is being reflected back at them? That antenna tuner. So one of the things that you have to be careful about when you select an antenna tuner, you have to know what kind of operating power you're going to be using. If you're going to be running barefoot, a 100-watt antenna tuner will do just fine. If you're going to run a kilowatt, you need to have, and you run into, that 25% now turns into 250 watts of energy you have to dissipate. So you have to have a sizable antenna tuner to dissipate that stuff. And then when you get up to a full legal limit, it gets even worse, a whole lot more, because there's a lot more heat that you end up having to waste there. So, Paul, did that answer your question?
Yes, the only thing that it didn't cover, which is fine, is the difference between having an antenna tuner at the shack versus near the feed point. And if there's any difference in loss, or if it's pretty much the same.
How would you call that one?
I think that there's less heated coax going to the antenna tuner when you have the tuner at the feed point, but I don't know if it's more effective of an antenna system.
Yes, it is actually more effective. Where you really want to put an antenna tuner is out there where you got the problem. If the problem is at the antenna, which is you're trying to work a part of the band that it was not really designed for, or not natively resident in, that's the place that you're going to want to end up fixing the problem. You're going to want to fix it at the antenna, not the coax. You're making the assumption the coax is doing exactly what it's supposed to be doing, providing a 50-ohm impedance.
Thank you.
Good question. Good question there. Okay, so let's every once in a while I like to do a little techie things, but I'm going to keep this as painless as possible. So a couple things on how you measure impedance. One of the little diagram on the lower left there is known as a return loss bridge, or actually a bridge. And that guy, that little schematic there is used in all kinds of devices. And there are a bazillion derivations of this concept on how this works. So what I have drawn there is the simplest way of expressing a return loss bridge. And all I'm doing is showing a battery. You have point A there, the current flows equally, or hopefully equally, into two resistors. And then on the other side of that bridge, you have two things. You have what's known as the, like R3 there, that's your standard. That's what you're going to try and match to. So that is your reference standard, that R3. Then R4 there, that is your unknown quantity. That's what you're trying to calibrate to. So there's tons and tons of different kinds of instruments where you need to do calibration that uses this very good concept, where you have calibration standards, like let's say a resistor at this point in time. So that's R3, and then you have some kind of variable resistor or variable component that you're then trying to take and match to and make it exactly right. So many calibration labs use this exact point. So what you're trying to do is look to see if point B at the very top and point D, when those things are calibrated and equal, that unknown is equal to the standard. The voltage across point B and point D should be 0. There will not be any difference in voltage. So that's a basic standing concept that I learned when I was a kid, when I was getting involved with electronics, and that I constantly run into that when I look at calibration standards and how to compare different kinds of things. So now RF is not a DC component. RF is an AC component. So we have to look at it just a little bit differently, but we use exactly the same principle that is known in this bridge. So if we go to the right side, the schematic there, we have RF coming in, which we know is AC, or alternating type of current. We have, and a bunch of other stuff that goes on with it. And then we have two resistors that split it. And mind you, all these resistors here are incredibly high precision resistors. They have to be super, super high caliber resistors that they use in these kinds of circuits to verify that these things are really, really precise. So R1 and R2 are the same as R1 and, excuse me, R1 and R3 is the same as on the other schematic for R1 and R2. Now, the reference resistor on this drawing is good old R2 down there. So let's say that will be our 50 ohm resistor. Now we know things are actually AC. So what we do is that jack J2, where it says RX, that really should be device under test, DUT. When anytime you see the acronym DUT, that stands for device under test. So you're going to connect your antenna up to that port there. And then you can connect up, like, let's say, a spectrum analyzer to that J3 port. And in that spectrum analyzer, you can see exactly how, as you sweep through a set of frequencies, you can see how the impedance change on that J2 port in reference to a 50 ohm load. So that's just the way that they do it for AC type of components. Very simple little way of doing things. So if you know the mismatch between impedance, then you can calculate the SWR. So if you know the delta between forward and, or excuse me, if you know the difference between what you have for impedance from a 50 ohm load, there's a set of calculations you can go through to derive what the SWR is. And I'm not going to bore you with those calculations. So let's take another way a look at how things are measured for if we want to know the SWR. The big picture of the meter there is a very, very common meter. You will find this in all kinds of MFJ type of devices and many other type of devices. It's actually two meters that are combined. One of them tracking the forward power, the other meter tracking the reflected power. Now, it just so happens because it's a ratio between the two different, between forward power and reflected power. It's a real easy set of math to take and derive what the SWR is, what the standing wave ratio is. And you can see where those meters cross, it crosses right at 2.5. So you have an SWR, all those red veins there all represent different kinds of SWR. You can kind of see you know, the SWR, when you have reflected power of down to 0, you have an SWR of 1. And as you can see, as that reflected power keeps coming up, there's a curve there, and where those meters cross each other, that will show you the SWR. Very simple. These are really great meters. And here's a little bit on some of the circuitry you might find behind it. The box on the left there is kind of a little external SWR. This means you don't have to pipe all your coax over to where you have your metering done. This is maybe like kind of a remote unit. So it sets the two 239 connectors there, connect into get seriesed in with your coax that is going out to your antenna. You can see that there's actually a piece of coax in there that goes through a toroid that's wrapped with a bunch of coils. That's nothing more than a transformer. That transformer there is really used to detect the forward current. And then there's kind of a aluminum brick in between there. That brick is intended to keep any spurious flux, magnetic field from either one of those transformers affecting each other. So it provides a level of isolation between those two. Then you see the toroid on the right side. Again, pretty much the same kind of thing, a little piece of coax going through the middle of it and a bunch of wires wrapped around it. And then there's a little circuit board tacked on the bottom there that probably has a capacitor and a diode on it too. So anyway, they have two BNCs out there, so you can tap off and you can see exactly what the forward current is and what the reverse current is. Over on the right side is a little bit of a simplified diagram of exactly how that works as far as the type of transformer, how it's wound, little diode for doing rectifying things. And depending on what direction you're picking things off of that transformer there, you can look at your forward RF current and you can look at your reverse current. And in the previous drawing where you had 2 meters, those two poles just go to two meters, just like what the rest of the drawing is there on the bottom. Pretty darn simple for a simple detector to figure out if you have reverse current or forward current and how much. So let's wrap it up here. Typically, we always use good old 50 ohm coax for everything we're doing. This example here does not necessarily cover all the things that there's a lot of similarities if we were talking about ladder line as far as there's a little bit different way of metering it. There's a little bit different way of looking at ladder line, but all the same principles still apply as far as SWR that you might get on ladder line and how you deal with it. All the components in your transmitter and antenna system should match to 50 ohm impedance. If there is any mismatch to the 50 ohm impedance, you will have reflected power. Reflected power is power that does not radiate from your antenna. It kind of gets trapped inside your system there and ultimately gets eaten up by heat. Reflected power is expressed as an SWR. It's a ratio between your transmit and reflected power. Very, very simple. And obviously, the higher the SWR is, the bigger problem you have that you probably want to figure out how to solve. Solid state transmitters can start reducing the TX power if the SWR starts to exceed 2 to 1, and that varies between transmitter, maybe 2.5, maybe 3 or something like that. But they'll always have some circuit in there to try and make sure that the MOSFETs in there do not get damaged by too much heat. An antenna tuner will help protect the transmitter, but will not affect the loss of radiated power. And an SWR of 3 to 1, 25% of your TX power will not be radiated at the antenna. So another way, I guess I keep picking on 3 to 1. When you start seeing 3 to 1, you start ending up getting some pretty good losses there. And sometimes you just can't do anything about it. You just use an antenna tuner to keep the transmitter happy. Sometimes you might think about doing things a little bit differently. I'm fortunate to have enough real estate here where like on 80 meters, I got one antenna that's cut for the low band. I have another antenna that's cut for the high end of 80 meters. The same way on 40 meters. 20 meters is usually a pretty easier one to be able to handle and keep things in check. So that's the end of the program here. And so I'd like to open things up for any kind of comments or questions and stuff.
So Mike, is the SWR measured the same, whether it's a vertically or a horizontally polarized antenna? And does the ground affect the SWR in any way such that we should consider that?
The horizontal and vertical antennas is agnostic to, it doesn't care. The the effect is that with a vertical antenna, you have a different the ground effect will end up affecting the SWR. It'll change the impedance. So when you muck with the impedance, it'll end up mucking with the SWR.
That's particularly true with verticals.
Yep.
Because of the radials.
Yep.
Yeah.
The vertical is more sensitive to that, but it's not the vertical itself, it's just the ground plane that is pushing against affects things.
Right. Paul, Mike, I have a series of questions does anybody else have any questions before I launch into mine? All right. I've looked at this issue for quite a while, and I've never received a satisfactory answer. I've looked in a lot of books. I mean, I've looked at a lot of websites with so-called experts in the ham radio world, and I've looked at a lot of professional literature on really what's going on with SWR and why you'll burn up your final amplifier transistors or tubes. Yes, what you said in the very beginning about tubes being tougher, about not really being affected that much by high SWR. That's not necessarily true. I burnt out. I don't know if you guys can see the rig. Let me see. Can you see the rig back here? This is a Yaesu, FT101D or Delta Z, and it's about 40 something years old now. It's a hybrid radio. It's got transistors and tubes. So the tubes are there's two. There's a driver tube, and then there are two power amplifiers, 6146B power amplifier tubes in that rig. I blew both of those one time by trying to tune, and I'll get into the difference between tuning on a transistor final amplifier versus a tube. But I was tuning, and assuming that these guys were really immune. Apparently, I had a very big mismatch, and lo and behold, I blew the entire, not to the point where the fuse blew and the whole radio went off. When I got it to, replace the fuse, turn it back on, it was dead. I mean, it was like dead. I mean, I just got hit. I just got static. And
so, quick question, Scott. Well,
yeah.
When you were trying to tune the thing, were you watching the grid current on those tubes?
I was, but I was very, very new at that, and I didn't really pay attention the way I should have, because they give explicit instructions on the way to do it. There's a technique. You have to do it very slowly and bring it up very, very slowly. But you're right, Mike. I did have too much grid current. But the point was that, and I didn't have a tuner. So what happened was, apparently the grid current was, the mismatch made it to the point where it wasn't because I was I was bringing up I think the grid current too fast. I think there was just such a bad mismatch that the final the pi network that is the interface, is the tuning circuit really between the final amplifier tube and or at least the feed line. The mismatch with the impedance at the output of the pi network was so, not 50 ohms, that it didn't it drew too much grid current or current in the tube, and I just blew the tube. Probably the plate current was way too high. Do you agree with that?
I agree. I mean, the older tubes are much more forgiving, but it's not a perfect world out there.
No.
And I still know that, back in the old days, well before I was involved with any electronics, there were guys that, tuning or trying to take and make a set of bed springs or gutters work and stuff like that, and they got away with it. But it's still not not absolutely given that you are totally immune to problems. Just like what you said, if you had a load that was an impedance that was way low, rather than 50 ohms, it was down around 12 ohms.
Right.
You're going to end up pulling more grid current. If you don't watch that grid current, you're going to take out your tube.
Yeah. So that's really what happened. So there's yeah, you got that. And then with transistors, the reason why they had to eventually add protection circuits to cut the power down if there was if you know the internal SWR meter detected a bad or a big mismatch was a similar effect. You would so this is going to dovetail into the issue of the reflected power. So the question I have is that reflected power. Am I injecting or does that come back to the transmitter if you don't have a tuner in between? And does that power get back into the final? You know, all you've really got between the transistor now and the coax connector on the thing is a balun,
Yep.
right?
Mhm.
It's usually a 4-to-1 or something like that.
Mhm.
But you'll get if you can get a big surge of current that will flow back in, that can easily blow the transistors. You know, it doesn't take a lot to exceed their power rating. So. Does that power get back? I mean, is it? I've read it does not get back in. It's you know I never got an explanation if the power doesn't get back into the transmitter and you know to blow up your transistors, then what is going on? Because you know I never there seems to be a controversy of people who know and really don't know and think they know, and they give you all this information and then you get incorrect information, but I've never seen the real correct explanation. So I don't know, even on all the handbooks I've got, nobody seems to say what's really going on there. So
Yeah.
maybe, did you ever come across anything like that?
I've come across, and I have to say the best explanation that I've got is that reflected power, the only thing you have is basically a coil that you're basically matching to, and that power basically is just because there's no diode or anything there to stop it. And so
Right.
you have that power that's coming back into it.
Yeah.
Now, the challenge is that I don't know if that power is coming back in phase or out of phase
Mhm.
to what it's trying to transmit. And that, I believe it's not in phase, and then that ends up causing the power transistor to think that it's not putting out enough. And then that ends up stressing it, thinking it needs to have to put out more, and then causes
Yeah.
overheating.
That's true. And plus, people talk about you can get very high voltage buildup if the SWR is really high
Yep.
uh, at the terminals of the transmission line. So that high voltage can also zap things like transistors. And so so yeah, in the days, the early transistor rigs before they, realized that you really need a protection circuit, there were no protection circuits. So if you didn't have a tuner and you weren't careful about matching everything up, you would have blown your final transistors in the rig, and have to send it back for repair or try to do it yourself. But that was a big problem, I think, in the early days, and then they added later on the protection circuits. So that's what we have to help us out. But the problem is, what will happen is it'll reduce your power. So you could be trying to transmit, and like Paul was asking, should you put your tuner out at the feed line, or is it the feed point of your antenna, or should it be in the shack? And the answer is yes. If you can get a tuner out to the feed point of the antenna, that's where you need it, because once you've done that, then then it will match the end of your coax to the antenna, and then you'll have 50 ohms. In other words, you won't get reflected power back down the coax.
Right.
So, and that's what you'd love to avoid, because if you have it in the shack and you don't do anything about at the feed point of the antenna, you're going to get that reflected power coming back like you talked about, Mike, and it will actually end up as heat inside the tuner. So that's the question. If you didn't have a tuner now, took the tuner out, that reflected power goes back into the transmitter. So there's heat, there's power that needs to get burnt up, and that power can burn up your transistors. So
Mhm.
uh, but there's, like I said in the beginning, I've never come across anybody who's really explained it. Walked you through what happens when you get a really bad mismatch. Why do you blow up your rig? and then once you know that principle, then you can really be conscious of the fact you have to have a tuner
Yeah.
somewhere in the circuit.
I don't
Unless
know
everything's
anybody
perfectly
who's
right.
done a lot of operating who hasn't blown up their finals.
What's that?
I say I don't know anybody who has done a lot of operating who has not blown up their
Oh,
finals.
yeah, I
Because
guess that's
a
true.
bird can come and sit on your antenna and you'll blow your finals.
Yeah. Well, that's just it. It is sensitive to the antennas are sensitive to the environment. And to answer Paul's question, yes, the ground does have an effect in some ways, especially with verticals. But if you've got low NVIS dipoles, as an example, or horizontal antenna, it's going to the local ground will have an effect on the the impedance at the feed points. So in that case, you have to be aware of what. That's why we have antenna analyzers, so we can see what that is, and then make sure that we adjust for that. The best solution is to have some sort of a tuner at the feed point, but for dipole, that's not going to probably work.
Mhm.
For a vertical, yes, it can easily be done, but so the next best thing is to just try to I guess work around it. For instance, I have a dipole out at LC. It's an 80-meter dipole NVIS antenna, and it's like Mike was saying. You need like really three different antennas to get across the entire 80-meter band. It's a very, very big difference in impedance between one frequency to another. Um, and so I have ladder line coming down from the feed point because ladder line is very low loss, and so there's going to be a higher SWR on the ladder line. It really won't be as bad as you think because Mike, you were alluding to the fact that you get loss, and I think a lot of you guys know this that the reflected power is going to be reflected back and forth along the feed line. It's going to bounce off your tuner, go back up to the antenna, come back down. So it's going to make multiple trips, and what ends up happening is it gets burnt up in the feed line, so you lose power just from heat in the feed line if the feed line is lossy. But if the feed line is not so lossy, then you won't really burn up that power, and eventually they say this is the other controversial part that actually that 25% power eventually does get out. You know,
Not all of it. We'll have a
I know
lot of,
not all of it, right? But that's the lost stuff, okay? So
Yeah.
that's the other point, Mike, that I wanted to say that I've heard that story that they say, oh no, you don't. That 25% will eventually get transmitted out if there's no loss. But if there's loss, which of course there's gonna be, you'll burn that up because it's just gonna get bounced back and forth, millions of times, and then get burnt up on lossy feed line. Ladder line is very low loss, and in the old days before World War II, they did use ladder line, and so they didn't worry about. They didn't even know what SWR was. I don't even think that concept was even understood. It was understood. I have a book to prove it. That written in 1932, where there was a whole chapter on that. But it wasn't a problem for hams because most people were using, almost everybody was using ladder line or even just a single feed line, single wire line, and they didn't even think about losses because there wasn't a problem. Coax, on the other hand, does have a much higher loss. So that when people started burning up their coax, then they realized maybe they better consider SWR. But ladder line, that was never a problem. So anyway. So there's a lot to it. It's a very, very complex problem. There are books written on it. Maybe I need to get a hold of one of those books and really, delve into really what's going on. But I've seen people talk. They've actually counted bounces and looked at the buildup of voltage at each bounce at each end of the feed line, and I've seen those kinds of calculations done. But nobody says what happens, really to your electronics when and why you're going to risk destroying things if you are not careful. So anyway.
Yeah, the SWR, the reflective part of it, think of it as an echo. If it bounces off of one end, it can also bounce off another end too.
Right.
And so that will bounce back and forth across your feed line via coax. And one of the things I didn't bring into this entire discussion, as kind of a separate one, is the losses you encounter by different types of coaxes and the length of those coaxes.
Right. But anyway, it's a great. Thank you for bringing up the topic because it's a great topic. I hope maybe if I learned something useful I can maybe do a follow-on do a presentation one of these days about what, really what's going,
Fun.
yeah. It's
So
an interesting topic because you get into reflected waves and all that. Um, and I don't know if you guys have ever seen this. There's an old YouTube video. Well, YouTube is not old, but I mean an old video from the 50s that is available on YouTube from Bell Labs. And I can't remember the gentleman's name, but he was an expert on impedance mismatch. And he demonstrated reflected power in a mechanical system because it's not just, it's not just electronic. It's any wave phenomena. You'll get reflection. You can get reflected waves, and you'll get standing waves and all that, and you can calculate standing wave ratios. But he showed on a mechanical system how there was like a change of mechanical impedance, a sudden abrupt change can cause a reflection, and how the reflection occurs because you get either a positive reflection or a negative reflection. And you can really get into a lot of complex mathematics with it, but it's a really good visual demonstration of reflected power at an impedance mismatch. And in this case, it's mechanical. Like I said, it's a track where he has a torsion, and he launches the torsion wave. So you see these. It's like kind of like a railroad track, and you see it that's suspended, and then you see the little cross ties, moving up and down as the wave passes, and then it reaches a point where the tension is different after on a second railroad tie that's tied to the first one, but it's got different tensioning on it. So that's like a different impedance, and the wave bounces back, and some of it feeds forward. Just like you've seen, in the technical material that we have to study for general class, as an example, or extra class. Um, so the phenomenon is demonstrated there, and then you can actually see visually what's going on. So it's very interesting. If anybody's interested, I can send you a link.
So another thing, just to add a little more complexity, is that we know like PL239s and different kinds of connectors on coaxes, or if you change from one kind of coax to another coax midstream, just to try to get RF out to an antenna, any of those little deviations there can also introduce a change of impedance and then also build up its own set of reflected power.
Yeah.
So there can be multiple reflections going on throughout that coax, not just from one single source.
Right, exactly, and that would be the thing. So if you have a defect in your coax, that can act as a impedance barrier. Things like that.
Yep. Another good one is if you run high power and if you have a steep bend in coax and that center conductor gets hot enough times, it will actually melt some of the dielectric and then actually move and thereby change the impedance as the RF makes that bend in the coax. So that's another source of of problems. In fact, uh, it used to be before they came up with some of the newer dielectrics that we have these days. There were lots of ways that darn center conductor could wiggle around inside that piece of coax and end up shorting itself out to the shield. Try to find that one. That's one of the reasons why a lot of our more sophisticated antenna analyzers have the ability to determine uh, where the fault is in the cable. You can find where the short is, or you can find where there's an open, and it will tell you distance from where you're testing from, where that is, and you can go out there, snip the cable in two, and find that, oh, a center conductor moved around there and shorted to the shield.
Right. Yeah, if you get a SW, if you measure your SWR and you find out it's an infinite, then you know that there's either a short or an open, because at a short or an open, you get total reflected power, and total reflected power translates to infinite SWR. So if you see that and you want to find, and you've got a very long run of coax and you want to see where that particular defect might be, could be at the connector, most likely, but it could be somewhere in between the two connectors at the two ends. So then you can, like a MFJ was a 259, the non-scanning type of SW or antenna analyzer has that capability as an example. And I think some of the scanning ones do too, right? The rig experts.
Yep.
Yeah.
Yep.
It's a time of flight and they send a pulse and they measure how fast it,
How fast it comes back.
yeah.
Wow, this is really cool. I love how this sort of just swirled around and spawned other discussions. This was really good. I mean, what a great discussion. Mike, you spurred on some great conversations, and I think you see some nodding heads going, yeah, been there, done that, burnt out a few of these, did that.
Yep.
And so it is something that is an esoteric kind of, you can't see it, but you can see what happens when it goes wrong
Mhm.
kind of things. And so great topic. Appreciate the education. Great response from everybody here. Thank you.
You're welcome. And even a simple little subject like this there's a lot of depth to it.
Yeah, there's
Excellent.
a lot of technical information that's buried in it, you know.
But I try and keep it simple. If I don't like getting too much into too much technical stuff, or otherwise people start nodding off and I lose them. But I think just enough little technical, a lot of practical stuff, and hopefully there's enough bullet points in the summary that people can remember those things.
I think there's a lot of relationship to interpersonal relationships, because if your lines of communication are not well maintained, there can be a great deal of communication friction in a relationship.
Are you saying there's a mismatch between you and a significant other, Andy? I
Well,
mean, because there's
sometimes
That's a great,
like,
that's a great analogy.
I've experienced.
Yeah.
A little SWR there, and it's all expressed as a ratio between input and output.
yeah, but a wallet can fix the SWR to bring it back to normal, and peace will reign.
Sometimes, yeah,
That's your tuner.
yeah. So
All right.
I'm constantly amazed at the analogies of ham radio and my world of personal relationships.
Yeah, I never thought of that that analogy before. That's a great, you can use that as a metaphor.
I think Andy owns the next topic on how ham radio relates to real life.
Yeah,
I
right.
think that should be a really interesting topic, Mike. I think
Yeah.
we should challenge him.
What
Hey,
ham radio really means, right?
I'll mention a couple of good things. This week here, I've been gone. I've been traveling almost most of the summer, and all kinds of stuff going on for me. But this was the first week that I've been actually back home for quite a while. And 10 and 12 meters has been an absolute joy all week long. And I, one of the things guys keep sending, for me, I'm a DXer. I'm trying to get off the North American continent. Anything going on the North American continent, that's nice, but I'm really not necessarily that interested in those things. But I keep getting emails says 10 meters open. Is Europe there? No. Well, this week when I say is Europe in there, I'm getting yeses. And so it has been a very good week. And I'm still working on my 5-band DXCC. I still have 10 meters that I need to finish up. It hasn't been open in it forever. And then also trying to finish up a 5-band on 12 meters too. So 12, 17, and 30. So I can get those certs. And so
Good luck with that, Mike.
yeah, so no, I made some good headway. Good headway this week. But I did get one entity that was added to my overall DXCC, and that was Liberia.
Oh, wow.
And so I was really happy with that. There's another guy out there in Angola. I've been able to work him on all kinds of 10. I didn't get him on 12, but 15, 20, and 40 meters the other night. And so that was really nice, knocking him off on all those particular bands.
What is he?
Angola.
Oh,
Angola.
Angola.
Yeah.
Wow.
So So anyway, it's nice to see the high bands, 10 and 12 waking up and getting some real production out of it, rather than fighting through stuff that you already got before.
Very cool. Awesome. Well, great meeting, everybody. Great presentation. I'm gonna do my best to keep pushing forward on the things that we know we need to fix and identify how we can collect our information. Take all these things. It won't happen all at once, but I am working on it. Let's have fun in the process. Let's learn and let's get together more often than we do in person. I think that's an important key for keeping this going. And thank you.
Thank you.
Thanks, everybody.
Yeah.